Okay, so thank you. Our final session is hydrogen in aviation this afternoon. And therefore, I'd like to invite our speakers to the stage. So we have Jean-Philippe from Airbus, Bart-Jan from Conscious, Jonas from H2Fly, and Sandeep from Zero Avia, and Linda joining from EASA. Thank you.
Okay, thank you, Colin, for inviting me on this stage. As Conscious Aerospace, we're honored to be here. My name is Bart-Jan Riedijk. I'm leading certification. Of course, I'm going to tell you something about the HAPS certification challenge. Conscious Aerospace, we're a new company. It was founded 1 year ago, but there was work up front. I'm going to explain that. What are we going to do? We are going to do a hydrogen propulsion system, HPS we call it, from tank, liquid hydrogen, and fuel cell electric based up to the propeller. And we want to do conversion of aircraft, retrofitting existing aircraft. In this case, the first aircraft we will do is a Dash 8-300. It's of course the CS25. There's a context to this company. And that is in the Netherlands, the government has decided to invest 20 billion euros in the period of 21 to 25 to establish a future sustainable earning capacity in the Netherlands. And from this 20 billion, aviation has got 383 million euros to make aviation sustainable in the Netherlands. And our project is the biggest one in that for almost 90 million. Of course, we have to match it as industry. And we are altogether 12 partners from the Netherlands. It includes the institutes like the University of Delft, the Netherlands Aerospace Laboratories, and other companies as well. The other thing is that we worked closely together with de Havilland in Canada for the Dash 8-300. And the project is called HAPS. It's a hydrogen aircraft powertrain and storage system. That's how it's called, but the product is an HPS, as we call it. So we have an existing aircraft. It has its own 3 TCs, of course, for the propeller, engine, and aircraft. It will be a significant change because we remove the combustion engines. We modify the aircraft. We have to prepare it for installation for an HPS system, and you install that. At the same time, we're a new company, so we also have to build a DOA organization for that. And in the end, you will have an STC for the aircraft, a TC for the HPS, that's our approach as an engine, and TC propeller will remain the same. We have no intention to replace the propellers as well. The planning, reasonable. By the end of 2028 would be the certification date. So the proposal, how to do this. So we want to implement the hydrogen propulsion system as an engine to the aircraft, so it will have its own TC. That's our proposal towards EASA. It goes up from the tank up to the propeller. The rationale behind it, it's an energy chain. You start with liquid hydrogen, you make it gaseous, you bring it to a chemical reaction, then it will be electric, you distribute it, it will be from e-motor, from electrical to mechanical, and it will go to the aerodynamics. Of course, for the aircraft's modification, it will be an STC. We have de Havilland Canada to support us in that. Of course, the effects of hydrogen, as the previous speaker mentioned, all kinds of effects, we have to take that into account. The HPS will be installed as a power plant. And how we want to go to the market is, of course, the building block approach. So there will be a demonstrator with 1 hydrogen engine and 1 combustion engine. Of course, we need an HPS TC from EASA, and then modifying the aircraft as a TC under EASA and/or Transport Canada, and then export the Dash 8-300 to operator countries. Mainly they are outside Europe at this stage, because it's an existing aircraft from the 80s. So, of course, how do you get the certification base? Basically, today it's a known process. In 2015, I did the application for PLV, a flying car, which is a gyroplane with road use, and then it was immediately application. And then we needed a lot of years, I think 6 years, to come to a certification base. So today we have the innovation partnership contract pre-application application, which I think is a good improvement to do all the conversations. And HPS is novel. So what I experienced in the previous project, you need a lot of conversations. It also requires learning, mastering new technologies, but that's your building approach, reviews, all that kind of things. There's a whole toolbox for that. What you also see is that you have to educate specialists in the CVs as well, because it's novel. Of course, understanding all the failure modes. You do that by testing or imagination. Also, certification base. It requires public consultation when you get into a special condition. And there's more. There's more. So there's a lot of things we have to do. We started with the innovation partnership contract. We're currently discussing it. So that started. So we really started with certification. That's my perspective, although it's a pre-application process. So in the end, the certification challenge, where you can think about Conscious Aerospace, new company. It always starts like a startup with funding. You need money. That's the first thing. The second thing, you need people, of course. A lot of people for this. Resources. It's not easy to find, but we'll do it. Of course, technology. We'll have a lot of testing we have to do, and design, and do all these kind of things. With the support of the technology institutes in the Netherlands. And of course, in the end, you have to demonstrate performance and safety. So this is for Conscious. On the other side, you have EASA. It's a similar story. They have yearly budgets, which is clear, but they always complain it's not enough because their tasks are growing. That's the discussion in the last few years of this kind of conferences. Of course, resources, same story. Too much to do, lack of resources. Everybody's looking for people, of course. Technology, the difference is a little bit, we have to master the technology and EASA has to understand the technology. That's the difference, I think. And of course, EASA, there for the special condition, level involvement, and decrease, all that kind of tools they have. So in the middle, we have to meet each other. And that's what I call the conversation arena. We have to have a lot of discussions. And I think the essence of all the conversations is, it's about dancing. When one moves, the other one has to move as well. And you like to do it in a fluent way instead of a staccato way. Yeah? And I think that the discussion we had before lunch, I think that touches all the elements to make it smooth, I would say. And I think that's the real challenge we have ahead. So, it's all about timing. That's what dancing is about. So, that's a challenge, and I would say, let's dance.
Thank you, Bart-Jan. Jonas?
Yeah. Okay. Thank you, everyone, for being here. Thank you. Special thanks to Colin for having us here in EASA. Again, in certification challenges of hydrogen propulsion. My name is Jonas Büttner. I'm from H2Fly. We develop hydrogen powertrains for aviation, the same as here, Avia in Conscious Aerospace. And yeah, I thought, as I'm here on behalf of my boss, I thought, as I'm a safety engineer, I'd do it a bit more technical than strategically. And this is my presentation now. So for the beginning, a quick overview. 3 years ago or 4 years ago at university, I already looked at regulatory coverage of unconventional powertrains, so electrical powertrains, but then also fuel cell powertrains and hydrogen-based powertrains. And yeah, it's obvious that by special conditions or CS25, we haven't covered fuel cell systems yet. We haven't covered any HV power management, especially high currents and high voltages yet. And also, which is a smaller aspect, the emission requirements. What is partly covered are LH2 fuel systems. We still have a liquid fuel. If we talk about liquid hydrogen, it's cryogenic, well, but it's still a liquid fuel, and we have a container, more or less, which is our fuel tank, a douar. And so some of those regulations which we can find in CS25 are still applicable. Now, what is the major concern concerning hydrogen? It's basically the explosive atmosphere. Everywhere where we have a failure, we can create an explosive atmosphere at the end of the day, and this is the biggest challenge with H2 using as a fuel in aviation. So here I just have some occurrences that can happen, failures that can create an explosive atmosphere. And our first safety cage, our biggest priority is to prevent those leakages at any time with early detection of any malfunction of the system. On the right side, we have a broad overview of the fuel cell system. Basically, every system can create some hazard to the fuel cell stack itself and create a malfunction, so that we, at the end of the day, have either a cross leakage from anode side to cathode side, that we have a creation of an explosive mixture, or we have even leakage out of the stack. So what if this doesn't work? What if we cannot prevent any leakage? Then we have a second layer of safety, which is the prevention of an explosive atmosphere. On the right side, I have some facts about hydrogen. We have a very high flammability, from 4 to 74% volume percent of hydrogen. The explosion limits are from roughly 18% to 59%, and a really low ignition energy of 0.02 millijoule. This is 10 times less than for a conventional fuel like Jet A1. So what is the problem with the prevention of the explosive atmosphere? At first, it starts with the H2 detection. We need reliable sensors. The sensors right now need roughly 3 seconds to detect the hydrogen reliably and say this is the exact concentration. We have problems with the diagnostic coverage. The H2 detectors are quite sensitive to, they are cross-sensitive to other trace gases, for example, and especially, for example, to humid air or water droplets, and then show wrong results, which might then, at the end of the day, affect not safety, but reliability. If we talk about certification, it's always like a trade-off between safety and then reliability of our system or availability of the system. Then we need, of course, if the H2 detection system detects something, we need ventilation. We have either passive ventilation or active ventilation, or in best cases, a combined ventilation. Right now, we say, as the ignition cannot really be prevented because the ignition energy is so low, that in any atmosphere above 4% volumetric percent of hydrogen is considered to be one. Like, we cannot really say, does it ignite or not? We've seen incidences where we had, for example, a high venting of a fuel tank, and just because the venting energy was so high and we have traces like dust in the air, it creates friction and then ignites the hydrogen, and there is the fire. So right now we say probability is 1 for ignition, so the first thing we really need to take care of is not having a leak that creates an atmosphere above 4% volumetric. Right now we work with zones quite similar to ground-based facilities. There we know the regulatory framework in the EU is ATEX. In the US is NEC, because we also have some projects in US. This is just a quick overview. In Europe, we have those 3 zones here. Here we say it's very likely to have hydrogen in there during normal operation. Zone 2, for example, is only in a failure case that we see hydrogen there. The same is equivalent for the US, but there we just have Division 2 and Division 1. But at the end of the day, it's the same. So what's the problem with the leakage? Here we have 2 H2 sensors, for example, and while the H2 sensors, they need 3 seconds, and then read, for example, 2%, and within the area around the leak, we could already have an ignitable mixture of above 4% lower of above 4% volumetric percent, so above 100% lower flammability level. If we dig a bit deeper, I came up with this slide. So here we have 3 charts. One is the system pressure. For simplicity, I say we have system pressure of 4 bar in a pipe, for example. The second chart is the concentration, the H2 concentration, and the third chart is our system, which is either on or off. So we detect a leak. Our sensors say, okay, we have a volumetric percentage that is critical, and then we have a time delay until the sensors really detect, okay, this is, for example, the 2 or 3% we need to shut down the system. But then we have a delay of our safety mechanism, because if we want to have availability of the system, we don't want to shut the system down when we don't need to. So we might have some validation of the value, for example. And then at the end of the day, we also have a delay of the failure reaction. And all of this is just time that we actually need to shut down the system. And then as the pipe is still pressurized, it still leaks hydrogen, and we just need a lot of time to have the right dilution of the atmosphere. This one I stole from CS25 from EASA. It's CS25 Amendment 21. The current amendment, I think, is 27. It's not there anymore. I don't know why, because it's a great chart. I think it's just an overview with all the ignition sources that we can have in a fuel tank or in an aircraft in general. So this is our third safety layer, ignition prevention. This is really hard, especially with hydrogen. So this should be the last layer of defense, because we can not really validate if we are ignition-free, even though we use, for example, ignition-free equipment. Okay, to summarize, what are the safety targets? Primary safety target, prevent escaping hydrogen and also have a reliable emergency shut-off in case of a malfunction of a system. And secondary safety target is to eliminate all electrical and non-electrical ignition sources, have a sensor and monitoring concept, and ventilation concept. One last aspect about the LH2 storage. This is kind of a trade-off between rupture disk and, for example, safety relief valves. When the rupture disks pop, they empty the tank completely, so the availability is gone. Safety relief valves, for example, give us a bit of time because they keep the pressure. Right now we use pressurized tanks. In the future we might go to pumps. Okay, and I think time is done, but just a quick photo of our last test flight with a liquid hydrogen tank. We worked together with Air Liquide. There are just came up just some other safety concerns, for example, with the venting. What if we have a CS25 airplane with a massive fuel tank and it loses vacuum, for example, and we need to vent all the hydrogen? Then we create a hydrogen cloud that is potentially ignitable with even in heights of 300 meters. What impact does it have on other aircraft with conventional turbines if it's being sucked into the turbines? And yeah, just a lot of technical questions that need to be solved over the next couple of months and years, I guess. Thank you.
Thank you, Jonas. Sandeep?
Hi there. So I'm Sandeep Kaley. I'm representing Zero Avia. I'm the head of airworthiness. So today we're going to talk about the activities in the area of zero emissions and what we're doing to help solve the problem. So just to run through the agenda, to give everyone scope, we'd like to go through the background and solutions for zero emissions in aviation, an overview with a roadmap for Zero Avia's hybrid hydrogen electric engine, an overview of the objectives and results of our Dornier 228 flight test program, our powertrain certification plan, which everyone's probably interested in, and R&D and future plans, what we intend to do. So moving on, the real reason why we're doing what we're doing is the need for zero-emission aviation. So globally, there's a growing need for zero-emission aviation, as aviation is the fastest growing source of greenhouse gases emissions. The graph shows the growth in percentage of human climate due to aviation from 5 to 10% to 25 to 50% by 2050. This has motivated the regulators, such as EASA and others, and the industry to work together and aim for net zero carbon emissions by 2050, which is the goal for the majority of the industry. The climate impact of non-carbon emissions such as NOx and contrails must also be considered. So a scalable solution needs to be found and to reduce carbon emission and non-carbon emissions. So why did Zero Avia choose hydrogen electric hybrid powertrains? So we see four main technologies being discussed with the aviation at the moment, of which hydrogen electric is the only scalable zero emission solution that we believe. So if we start from the bottom of this table, which is on screen, hybrid electric has the most limited impact on emissions because of the continuation of turbine engine use. Then we move up to sustainable aviation fuels, which do have a moderate impact on CO2, however, are limited in terms of the impact on other emissions. There are also issues around feedstock sustainability and the cost of fuel. While hydrogen combustion eliminates the CO2 emissions, but still produces NOx, and is less fuel efficient than hydrogen electric engines, which we believe to be the only scalable and zero emission solution, with the only waste being water vapor. So as you can see from the screen, a hydrogen electric engine in every aircraft is our mission, and delivering a world of truly clean flight. So we are working with aircraft operators, manufacturers, lessors, and airports to supply the world's breakthrough zero-emission engines and the infrastructure and fuel to power a revolution in green flight. We are focusing on hydrogen electric powertrains, and this image depicts our mission of a hydrogen electric engine in every single aircraft, supported by an ideal infrastructure where renewable power is used to split water into hydrogen and oxygen using electrolysis, which is then delivered to the aircraft. So this picture on screen, it's Zero Avia is developing a four-engine offering, and it shows key aspects. It's an overview of our hydrogen electric engine solution. So it includes an EPS, which is electric propulsion system, with electric motors and inverters. A PGS, which is power distribution system, with fuel cell system, which converts hydrogen and oxygen to electricity with only water vapor as an emission. The system also includes the HMS, which is hydrogen management system with the hydrogen tank and manifolds. The air supply to the fuel cell is provided by a compressor. So I'll leave that on screen for a couple of seconds so you can see how the picture depicts what we try to achieve. So, well, going forward, so we can see all segments that we're intending to fulfill, starting with a 9 to 19-seater regional aircraft. As you can see on screen, we've already completed the first, which was the Piper. In testing now is the Dornier, a 19-seater. And we see this technology being applied in all segments. And as we've shown from going from the Piper to Dornier, we're working on continuously scaling and improving the technology. Alongside this, we're testing our 600 kilowatt engine powertrain. We are developing the next engine of class to be 2 to 5 megawatts, which is very, very, very powerful, to target the regional turboprop aircraft in 2027. Yes, it is ambitious, but we can do it. Which will turn and create technology pathways towards a larger aircraft in the future. So this is our product roadmap. You see what we're currently working on at the moment on the left-hand side of the screen, which is a ZA600, and our future ambitions by 2032, which is a ZA10000, the larger 10 plus megawatt powertrain. So this shows some detailed and technical commercial specs for the current and future product offerings, including shaft power, which we just spoke about, which you can see is incrementally increasing. The passengers that it can actually have on board, so starting from 10 to 20 seats to 200 plus seats. The range, which goes higher as you go across for the ZA600 to 2000. And you probably see the hydrogen storage. So at the moment, we are working on gas, but going forward, it will be liquid. And you see the fuel cell types that we're using there. So in the case of the ZA600, the target airframe includes the Cessna Caravan and the Dornier 228, which is actually geared towards CS-23 aircraft at the moment. So just to show you what we've actually achieved so far as a company and at the airworthiness team. So here's an overview of our test flight objectives and the results. So as you can see, our flight test plan involved the Dornier 228 with a hydrogen electric left-hand engine. We conducted a 10-circuit flight, permit to fly at Kimball Airfield in the UK, which the first flight was on 19th of January this year, and the last 10th flight was conducted on July 13th this year. Flights were conducted under a CAA permit to fly, and we tested airspeeds and altitudes, varying, different thrust and power settings, endurance, and go-arounds. So overall, the objectives achieved. The test campaign, we believe, was a success. We established a safe flight envelope. Our systems operated within the established limitations, and we had satisfactory handling and controllability. We had no in-flight shutdowns or terminated tests. So overall, we've successfully demonstrated the safety and viability of our hydrogen electric engine with this flight test plan. And I'm probably going to run over a little bit.
Yes.
So the certification journey. In terms of certification of our engine, the timeline involves Zero Avia being granted design organization approval by the agency. However, next, we need to apply for a type certificate for the powertrain, which will be the main objective, followed by integration of this type certificate into an STC onto the launch airframe, which I've mentioned is a Cessna Caravan C28B. And this will prepare the powertrain for entry into service. So, looking on screen, this is the certification plan for hydrogen electric engine or powertrain. You can see the certification plan is what I've just went through briefly. It's an STC for integration for a type certificate of electrical propulsion system and our power generation system. We know that there are special conditions that currently exist for the EPS, with certified products already operational in the market, which is great. The requirements for fuel cell power and hydrogen management system are under development, and we are in talks with the regulators and industry working groups. And our hydrogen management system will initially form part of the aircraft STC, but we would like to develop some ETSO or TSO standards, so these can be saleable and off-the-shelf bespoke items for some of our HMS components. And I think it's good for the business to have TSO-approved articles, which shows that they got TSO on them, or ETSO, or UK TSO, a TSO. So finally, and I'm running over time, so apologies, our research and development and plans. In terms of Zero Avia's R&D activities and future plans, and in the addition of the ZA600 design and certification, and to our hydrogen infrastructure solutions, we have achieved a HTPEM, which is a high-temperature proton exchange membrane, fuel cell technology breakthrough. So we've done a lot of that, and that's down in a Sandwich site in Kent. We've developed the world's largest fuel cell compressor, and we've made progress with high-power EPS, which is electric propulsion system, developments, facilities, and testing. So we've done quite a bit. Just because I've been talking with loads of acronyms, it's on screen. I think that's really good because aviation's full of acronyms. And so, yeah, thank you. So if you've got any other questions outside this conference, please feel free to email me. I will get back to you. And yeah, let's all work together and get this solution certified. Thank you.
Thank you, Sandeep. And then finally, Linda.
Well, yes, good afternoon, everyone. The last presentation of today, I understand, so I hope you're still full of energy, and I will try not to make it too long. Certification challenges for hydrogen. Well, we bring a new substance on board, new technology. So, yes, I think we have some challenges to tackle here. But of course, we want to fly in more green and more sustainable. And it seems that hydrogen, as also the previous speakers have told us, is a very promising candidate. The two possibilities that we see at the moment is either to use hydrogen as a reactant in a fuel cell system, which I depicted here in the little figure. And a fuel cell stack, you can see above is a picture of a larger fuel cell stack. The other way, of course, is to burn hydrogen directly in an engine. It doesn't really look so much different from other engines, so I just took a schematic to remind us how combustion engines normally work. And for hydrogen, it will be, in principle, a similar technology. Of course, as a regulator, as a safety oversight regulator, we are always looking for the hazards, for the risks, because we want to bring everybody safely from A to B in an aircraft, as also I think everybody else here in this room would like to do the same. Hydrogen has its own very specific characteristics and therefore their own hazards. I just put a picture here of one of the challenges that we will have to face. On the left side, there is a flame. You just don't see it. And this is one of the peculiarities of hydrogen. A propane flame or a kerosene flame, when it is combusting, you can see it and you can feel it also. Also, hydrogen is very small. It's creeping everywhere. Does too like to do that. It also like its friend, oxygen. And all this brings us to the small list I put here, which summarizes the hazards as we are foreseeing them at the moment. Of course, fire or explosion risk, I think, is on the top of the list to look at. But also mechanical and material hazards. If you are speaking about cryogenic, of course, it's very, very cold. It's around 20 Kelvin, which is really cold. But also, because hydrogen is creeping in things, it can also change the material. And this is also something that we will have to take into account when looking to put hydrogen on an aircraft. Are the materials that we are used to use today still sustainable in the future, after maybe a long time exposure to hydrogen, or even in case of hydrogen leaks in a shorter frame? Crashworthiness and ditching, I think it was already mentioned by one of the speakers before me. We have, of course, regulations concerning these, but what will be the effect when we put a hydrogen tank and a fuel cell system on board an aircraft? What do we, because it's highly explosive, as we can see under certain circumstances, and we still want to survive with the passengers. We also have physiological hazards. As I said, the flame, you cannot see it. The other part is you can also not really feel it unless you're very close, more or less in it, which is quite painful. And also you don't smell, you don't smell it or taste it. So if your aircraft is filling up with hydrogen, you will not notice until it's a bit too late and there's not enough oxygen anymore to survive as a human being. Cryogenic liquid hydrogen, I already mentioned, if it's coming in contact with materials, the material of course becomes very brittle because it's just freezing very much. And also for human beings, if you come in touch with this kind of cold substances, you get cold burn, which is also not so nice. And next to that, of course, there's fueling and handling hazards. If you are on the airport and we want to refuel the aircraft, how is this working? I've seen examples where people wanted to take the tank out and exchange it completely, or we just do like conventional aircraft. You put how do you say it in English? Thank you, a fuel coupler to it. How does this work, and what are the specific hazards in comparison maybe also with kerosene? Of course, as you mentioned, we have a lot of experience with that. At the moment, and also you have seen this in the previous speakers, we see basically two types of storage and distribution, either in a liquid form, which you can see here on the right very schematically, and of course the gaseous form. The gaseous typically is also high pressure, so it also brings some interesting new aspects over there. Of course, we know pressured air bottles, like for instance oxygen bottles, but they are normally quite small. And in this case, it will be larger, and of course also your propulsion will, in the end, depend on it. Having said all this, what about certification? Well, I think you can already feel, and also it was already touched by the previous speakers, the current certification specifications will not fully cover the fuel system and the introduction of hydrogen. Normally, as a regulator, we say immediately, special condition. So that's what we are looking for, to find a special condition that we can hopefully publish soon. And of course, with a special condition, we need also to tell you what will be our expectations, or what was the background in our mind when putting a special condition out. Of course, we already have we have some information already that we can use for such a special condition. I had the opportunity and the honor to work with the FAA in an ARC. Also, ANAC from Brazil was there, and a lot of companies willing to support us. And we did an airworthiness review committee, The title of this report is Energy Supply Devices, but when you start digging into it, you will see it's only about fuel cell systems and hydrogen. Next to that, we have several innovative partner contracts, or IPC. These are direct contracts with several OEMs, and I can tell you we learn quite a lot in these contracts. I hope vice versa, that there's also something that we can bring, and it's not only us learning a lot, but this is really, really very good, and we take all what we learn, of course, with us in a more generic specification, of course, because we will not be able to go into the details of the technical designs that are shared with us in these contracts. We also work together with the EUROCAE. EUROCAE and SAE, it's one group. It's already working for a very long time. They already have some standards that are out there that you can look and take to your advantage. And of course, we are also more recently engaged in research activities. At the moment, for instance, we have quite some projects with the clean aviation joint undertaking. And also from these kind of activities, we again learn a lot. Sometimes it looks like, hey, we do again a gap analysis. Hey, we sit again in the same kind of subject. But I mean, with every person or every consortium you talk to, they have a different view, they have a slightly different design. So I think it's still worthwhile to go through these activities together. We will try to go with a special condition to apply for different certification specifications. We have clearly activities in the 23 area, but also in 25 area, there's quite some activities. And then also, by the way, the drones, we should not forget, also they are looking to work with hydrogen and fuel cell systems. And then there is the ongoing debate. Also in the electric and hybrid propulsion systems, we see the same. What can we certify as an engine? What components can we put all together or not? Or should it be an aircraft type certificate, or should it be like a conventional one where we just have the propeller, the engine, and the storage? I think this is a quite difficult discussion to have right now, because we still have to learn so much. But of course, it's something we really have also to debate at some point. I'm also overshooting in time, I see. There's a red zeros here, so. As I said, we look at the special condition. Of course, it will be performance-based. We, at the moment, are considering to also name this energy supply devices, so that we can also use it, hopefully, for future applications with other energy systems. I will not keep you too long. The next steps for this special condition is, of course, we are internally reviewing the wording at the moment, and also what will be the best first route to go for. For the time being, we will cover in the AMCs fuel cell systems, hydrogen storage, maybe gaseous. We will have to discuss and to see what is the first need also from you, from the industry. I can only say to be continued. Thank you so much.
Thank you very much, Linda. Linda, thank you all. I think you'll agree, all very interesting presentations. So now if we go to Slido, and we already have quite some questions there. The very specific first one for Conscious Aerospace: is the hydrogen tank part of the engine certification or aircraft certification? I have to say, in your plan, I know it's very early days. What is your thinking behind this?
As I discussed, the hydrogen propulsion system includes a tank up to the propeller, because we want to control the energy transitions. There's latency in the system, so you want to control that. So the hydrogen part should be part of the engine certification from our perspective.
Yeah, and just to say on that, I mean, it's a question that we get from a lot of people that are in this area. How far can they go with engine certification? What can they include in the engine certification? And at EASA, it's something we're studying. We don't have the answer yet. It's something that we're looking into, and it will be one of the first questions that we address. And you will recall this morning we talked about terms of reference with the FAA, because it makes no sense if we decide on one thing can be part of the engine and then the FAA make a different decision. So it will almost certainly make up parts of the discussions under that part of the terms of reference, so that hopefully we can come to a harmonized output as to what we can accept into an engine TC for a hydrogen propulsion system. Okay, so the next question, which could be the STC classification in case of introduction of hydrogen propulsion on an existing CS-25 aircraft, TC significant or substantial? Again, this is a very good question. When somebody applies, we expect them to have done the analysis and to say, and then we will review their analysis and we will and we will come to a conclusion. So I would say it's a very good question, and it's the first question to be asked when someone proposes an STC. But as nobody has applied for such an STC today, we can't say 100% what the outcome of such a question would be. Okay, so the next question from Javi. So Zero Avia, please could you highlight on safety learnings, key points of attention for regulators, perhaps on your H2 propulsion system development so far? So Sandeep, is there something you want to highlight?
Well, we're doing lots of work with the CAI at the moment, the innovation group, the CAA, highlighting gap analysis of safety. At the moment, hydrogen is obviously not a well-known, we've got requirements-based reports to say how it interacts. So there's a lot of work, bench testing going on to find out the actual safety significance of hydrogen. To be fair, there's nothing really out there which is certified for hydrogen. So the key points and attention for regulators is teach as we're learning. So it's a both ways, it's a two-way street. So that's where we are so far, basically, in development, permit to fly, and hopefully certification.
Okay, and although it says Zero Avi there, I think this question is good for others, and I know they gave some. I mean, Jonas, from H2 Fly perspective, I know you highlighted the flammability aspects, but other aspects, or you see this really as the key?
It's not only flammability. We have a lot of different aspects which are quite difficult right now, and we still have a lot to learn on many aspects. So.
Okay. Okay, and then thank you. And then if we go to the next one, so H2 Fly, how do you propose to demonstrate a low flammability of the liquid hydrogen system in terms of explosive atmosphere in the tank? Do you have something in mind that you can share, or?
Yeah, sure. I can explain, but it's a bit technical again. So we won't see once the tank is filled and we have liquid inside. We only have a pure hydrogen atmosphere inside, and we don't expect, like I showed you the flammability range. It ranges from 4% to 75%, and we are at 100% inside the tank, so nothing is flammable inside there. But it's a good question concerning purging. We need to purge the tank. Once it's designed, you need to get rid of the oxygen or the ambient air which is inside there. So we have to either do a pressure swing purging. That means that we pressurize the tank to 6 bar and release the pressure again, pressurize it again with nitrogen to inert it. And then after that, we flush out the nitrogen with hydrogen. And then you have a pure hydrogen, or nearly pure. It's like 99% hydrogen in the tank, warm hydrogen. And then you crack open, for example, the liquid trailer and cool down the tank and then fill it up with liquid hydrogen. And once you have a pure hydrogen atmosphere in there, it's not ignitable anymore. It's only the time where you really have to take care is the flushing of the tank. And if you do a mistake there, you could potentially create a explosive atmosphere. Or you could go at first with liquid hydrogen in without properly purging it, and then you solidify, for example, air. And solidified air can also get ignited with liquid hydrogen in combination with the liquid hydrogen.
Okay, thank you. Very interesting. Is the aviation industry using synergies from the space sector due to significant expertise there? For example, cryogenic condition storage, material certification. Jean-Philippe, can you comment on this one?
Yeah, well, there are certainly synergies to be used with the space sector, but there are also limits to it. I would just take examples mentioned here. Storage, they are storing the liquid hydrogen for a few hours. So a foam insulation is enough for them. It will not work for an aircraft. Material certification and maybe material reliability. They are using hydrogen valves that must be functioning for, again, a few minutes, whereas for airplane, it's thousands and thousands of flight hours that he has to work. So yes, there are synergies, but there are also very much limits to the comparison we can do with the space sector.
Okay, thank you. And any comment from Zero Avia on that one? Are you looking at space?
So we're not really looking at space stuff at the moment, but we're just trying to get information gathering from automotive, maybe space, maybe other aerospace components, submarines, marine. So we're just looking at everywhere to get data and assess what's best and come up with a solution, or produce something to the regulators.
And Jonas?
Maybe I can add something. We have a supplier from space, and we looked into space, of course, because there the technology is developed. But finally, if you ask them about cycles, they say, cycles? 10 is enough for us. So it's not for aviation yet, because they use it 10 times and must say, okay, we are reliable for 10, maybe 100 cycles, but we look for 10,000, 20,000 cycles.
Yeah, it's a one-off solution. So
yeah, exactly.
That's why we don't use it.
Exactly.
Yeah. And Bartjan, in your because you have a quite vast network of stakeholders, are any of them coming from space or bringing?
Of course, the NLR has space experience, but it's also, I think it's always copy, adapt based, always. Look around and pick what you need and adapt it to the safety levels of our business, I would say.
Okay, thank you. So on to the next question. Hydrogen tank stroke engines present a high risk of explosion. External threats like lightning may increase that risk. How are these threats addressed? So Bartjan, have you started to look at, have you got as far to look at these threats yet? Well, your plan, I know it's early days for Conscious.
Of course, we've looked to all the threats, but not for the solutions yet.
Yeah.
That's the short answer, yeah.
And Jean-Philippe, anything you can say from Airbus research or?
Honestly, I'm not aware of the details, so that's certainly one of the biggest threats. Also, this one is existing for kerosene aircraft as well. So, no, I'm sorry, I'm not aware of the specifics.
No problem. Jonas, a H2 Fly, have you been looking at lightning threats or?
Yeah, definitely. It's a risk. We probably have a vent stack sticking out there exactly at the highest point, because we're gonna want to go out of the highest point. So we expect lightning strikes there. Again, it won't impact the tank itself, because we have 100% hydrogen in there. But obviously, it might affect additional equipment and valves and whatever. So that's an important aspect we need to look at and find a solution.
And did you have to do anything for your permit to fly in terms of, or was it more about picking the right weather?
No, they were picking the right weather.
Normally, yes.
So we haven't tried other conditions than VFR yet.
And Sandeep,
yeah, so Zero Avia permits fly is very limited, so it has to be perfect weather, low gusts of under 15 knots, no rain, no lightning,
No INC conditions.
no icy conditions, no fog. But going into certification, we'll have to address that sort of risks, and that'll be done maybe in the lab, maybe some flights. But as H2 Fly suggested, having the wicks on the side of the plane for the highest point for electricity to go in and come out of the aircraft. But yeah, there's not been addressed yet. But there has been, it's kind of assessed in the FHAs, failure hazards analysis reports. But yeah, this is a solution which is ongoing and probably won't be able to be solved in the near future yet, my understanding.
Okay. Okay, thank you all. So the next question, from Javi at EASA, H2 Fly, is it possible to share with EASA or further your studies in regulation applicability for LH2? Is this something you studied extensively?
Definitely. I actually wrote a thesis about it, so yes, I can share privately.
Okay, thank you. And another one for H2 Fly below, but looks on which platform was LH2 flight tested, and what were the test conclusions encompassing both challenges and positive aspects?
So the flight testbed was our test aircraft, High 4. And actually the test conclusions were very promising. We thought we run into troubles with connecting the fuel cell to the liquid hydrogen because we need a heat exchanger in between, and we thought maybe we're gonna run into some issues. Of course, while testing there are always issues, but nothing really related to this coupling between the liquid hydrogen tank and the fuel cell. That worked out pretty well and looks really, really promising at that point.
Okay, very good, thank you. Then one below for Zero Avia, by the looks at what are the expected challenges for applying STC on the certification journey? We can start with Zero Avia on this one, but I think...
Yes, I think the biggest challenge at the moment on our Cessna Caravan is crashworthiness. That's because we're modifying the aircraft on the belly of the aircraft to hold our hydrogen tanks. Fuel cells are conceptual architectures on the side or inside the cabin. We have to make sure the loading from crashworthiness doesn't affect the seat tracks and the seats. So the load path is a major concern for us. But crashworthiness is number one, which could affect the STC of the certification journey, and hopefully stays in the realm of what we classify for the change to be for the STC.
Yeah. Okay, and conscious, you're also looking at STC routes, so from your perspective, the main challenges that you see on the...
Yeah, I think it starts with mastering the technology and understanding all the failure modes, of course, in general terms. And of course, everybody thinks about the explosion type of things of hydrogen, crashworthiness, all that kind of things, of course. Yeah.
Okay. Okay, thank you. So the next question, has there been work done regarding accelerated hydrogen embrittlement from liquid hydrogen? So if we start, Bart-Jan first, or do you...
I'm not sure about the answer, but I know that the Dutch aerospace laboratories, they are doing material coupon testing with hydrogen type of things. But I don't know whether they're doing this effect, but they look at embrittlement of materials.
Okay.
They have a research program on that.
And Jean-Philippe, are you aware of any research in relation to this accelerated embrittlement from liquid hydrogen in particular?
Not necessarily a research, but I mean, reflecting on the previous question, I believe if there is a domain where we can learn from space sector, it's certainly this one, because they are storing liquid hydrogen, so they should have some experience on it.
Okay. Jonas, on your side, are you aware of research in this area?
We haven't done studies specifically, but we just kept using materials that are well known to work with hydrogen. So austenitic steel, aluminum, and we've never experienced any embrittlement so far.
Okay. Okay, and Sandy?
Yeah, it's the same with us with H2 Fly, so it's the same sort of concepts of carbon composite aluminium, pressure valves and so forth, but we haven't experienced anything from our testing so far.
Yeah.
Development in the future, we might see something, but it depends on the pressure and the capacity of hydrogen within the tanks and the way it goes through the pipes. We might even have some of this from the infrastructure, ground infrastructure, fueling the aircraft. So because Zero Wave is very in tune of the whole cycle, ground to aircraft to refueling, making our hydrogen and distributing it at major airports. So it could come about, but there's not much research being put into it at the moment.
Okay. And Linda, I mean, are you aware of any research? Clean aviation, I don't recall them specifically looking at this, but...
Not specifically looking at accelerated hydrogen embrittlement, but for sure there are plans to come up with more dedicated research programs. So it could maybe be one of the ones if it's foreseen to be very important. Somebody wants to have a microphone?
Mario?
Well, just to say that usually when we refer to hydrogen embrittlement, we are thinking about atomic hydrogen, then recombining into the material as molecular. But in this case, when we treat hydrogen as a fuel, it's already at the molecular stage. So usually we should not expect any kind of phenomena, except when related to cryogenic deterioration of materials.
Yeah, I think this was a little bit a part of the question as well, because it said specifically from liquid hydrogen. So yeah.
Yes, I'm afraid that liquid hydrogen we still have to learn quite a lot, to be honest.
Yeah. Okay. So the next question: how deep hydrogen engines affect environmental control systems of the aircraft? I'm not sure I fully understand the question, but I mean, I guess they're saying if you're putting hydrogen on the aircraft and the environmental control system for the aircraft are typically from the engine bleed, how that's then addressed. Is there something who start as Zero Avia? Is this something you've looked at?
Not at the moment. I don't think we've seen anything at the moment. I don't really understand the question fully, to be honest.
Yeah.
Unless whoever posted it can probably elaborate on it.
Yeah. Jonas, anything on addition?
If it's going in the direction you were suggesting, then I think our concepts will be that we keep out any hydrogen out of the cabin, have separated compartments, fuel compartments and fuel cell compartments, that we don't in any way interact with the ECS.
Jean-Philippe, from Airbus perspective?
I'm not totally sure to understand the question. If the question is, will an STC affect the environmental control system? Certainly, yes. If you are replacing a turbine by an electrical engine, you need a new system. But for an overall aircraft, I mean, there is already at least one excellent aircraft flying and certified with an environmental control system not related to the engine.
Yes, yeah, I'm certainly aware of electric systems taking ram air from and using, and I imagine that could be a route that they will go. But and then there's the thermal management, which is in any way critical on all these aspects that needs to be looked at. Okay, and then we have a final question, and it's so there are multiple alternates proposed for less emissions: SAF, hydrogen, electrification. Could it be better to select the most optimal way and focus on that? The question would then be, what is the most optimal way? And I think this is probably one of the reasons why we're looking at many different alternatives, and it may be that the optimal way may be different for different size aircraft. But it'd be interesting to get the panel's input on what is the most optimal way. As it's a hydrogen panel, I suspect which way it might go. But so I start with Zero Avia from your perspective.
This is hydrogen to hybrid electric. The best way forward.
But Jonas, from your aspect, have you studied other systems and?
I also go with hydrogen. in general, I think SAF, whatever way we want to produce it, it's super energy efficient. I know LH2, the liquefaction process, and H2 generation is also quite energy intensive. But if you go down the line, H2 wins, I think, if we have enough renewable energy. And SAF, whatever way we wanna create it off, it's just a lot of energy we need, especially if we think about carbon capturing.
Yeah.
If I can just add to that, sorry. So there's that table that I showed in the presentation.
Yeah.
You know, the hydrogen, H2 electric to hybrid. I think that graph speaks for itself, really, for our point of view, anyway.
Okay. And Jean-Philippe from Airbus, because you have a different perspective, you're not reliant solely on that.
If we think about the optimal way for the planet, I would say the optimal way is a combination of the three, because they will not be available at the same time. So maybe the less efficient one will be available first. So take good use of these ones before the next ones are coming and are even more optimal.
Yeah. And Bart-Jan?
Yeah, so we've chosen for the retrofit solution because that's short term, 5 years. It's possible to make current aircraft, although it's a specific type of aircraft, you can make emission free. That's a short term. And after that you will go into line fit new aircraft, new configurations. And of course it's Darwinistic, what we're experiencing, I think, at this moment. A lot of initiatives. Of course, small aircraft will be electric with batteries, and then hydrogen for a certain size of aircraft, and the SAFs for the really big ones, intercontinental flights. That's my guess. And that will evolve in the coming years.
Yeah. And Linda, from your perspective, your feeling on this?
Yes, my feeling is as well that at the moment all three have their own applications that are all three really valid. Electrification, batteries, they really have the weight issue, so I don't see it flying at this moment in large aircraft. Maybe in the future, but I think at this moment in time we should really pursue all three of them, and maybe there's still more coming, we don't know. And I think time will tell us what in the end is the best way, or maybe even all three still.
Yeah. And on top of that, there's the non-CO2 aspects where there's still quite a bit of research to try and understand what some of these solutions mean from non-CO2 and what is really the effect of the non-CO2 on the global warming. Yeah. Okay, we've run out of time. So I'd like to thank everybody on the panel up here today. It's been very interesting, so thank you all.
Thank you.